This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
That works. So our next speaker is Zhan, and he's going to talk about non-asymptotic approximation error bounds of parametrized quantum circuits. So thanks. Take it away.
Okay. Thank you for the introduction. And my name is Zhan, and I'm happy to talk about my work on the non-asymptotic approximation error bound of the PQC. And this is a joint work with research groups from Wuhan University and the Hong Kong University of Science and Technology. Okay, so, okay. So let's first describe this overall settings of the quantum machine learning. So today in our work, we will focus on the quantum machine learning model that takes a classical input and produce the classical output. And we will use the quantum models, but notice that the quantum model is not necessarily on the near-term devices. So, as we know that there are many types of quantum machine learning model depends on how we choose the types of data and the types of the algorithms, as the figure shows. And as I described, today we'll focus on the CQ type. And the ultimate goal of this kind of type of quantum machine learning model is to improve the performance of the classical machine learning models. Okay, so speaking of the possible quantum advantage of quantum machine learning models, we'll first discuss the essential aspect of the quantum machine models, because when we talk about quantum machine learning algorithms, we actually use a quantum machine learning model to, say, learn the function lies behind the pattern of the input-out pairs of the data, which means when we have a quantum algorithm for the quantum machine learning model, we can divide the arrows into three parts. The first is the training part, corresponding to the optimization, which characterizes the ability to efficiently coverage the global minimum. And the second part is the estimation arrow, which corresponding to the generalization ability of the model to adapt to the unseen data. And the second part is what we'll focus on today, which is the expressivity, which is the ability of machine learning model to approximate or say represent functions. Okay, so let's next to briefly introduce the quantum machine model, which is the parametrized quantum circuit, and PQC in short. PQC is a quantum analog of the feed-forward neural networks. So when we have a classical data, say X, then we will first to input the data into the data encoding circuit. And then when we train this quantum circuit, we just adjust the parameters in those trainable circuit. Then and the output is we apply this parameterized quantum circuit on the initial state. Then we do the measurement and take the expectation value on some observables as the output. So as we can see in when we talk about this PQC model, we can actually think of this quantum machine model as a function, say f theta x. And one thing I should mention is it is a data reuploading form. When we have data, we actually upload this kind of data inputs into the quantum circuit multiple times. So the form of this model can be right in this form. And as we said before, we will focus on the expressivity of the quantum machine model today. So the first question is that why the expressivity is so important for the machine learning model overall. So one may ask, why does the FNN work overall? it is because one of the reasons why it works is because it has a theoretical guarantee, which shows that FNN are universal approximators. And the universal approximation theorem tells us there always exists an FNN with one hidden layer and arbitrary width that can approximate any continuous function. So that is like the somehow tells us the expressivity of the FNN. And the next question is, how about PQC? And actually, PQC is also a universal approximator for square integrable functions, which is proved by Mershud et al. And the main idea is to use PQCs to represent the Fourier series of the target functions. And now we know that the FNN and PQC, both of them are like universal approximators, which means both of them have really great expressive power. But the problem is that is the universal approximation theorem sufficient for us to find like the quantum advantage? The answer is no, because the universal approximation theorem are more like the existence proof, but it's not quantitative. Which means we cannot use the universal approximation theorem to determine the necessary size of the models to achieve the desired accuracy. Which means that we cannot, say, quantitatively compare the performance between the classical model and the quantum model, which means that no quantum advantage can be obtained. And recently, in classical learning theory, a quantitative approximation error bound has been established in terms of the width steps and the number of parameters. For example, we know that there are like nearly optimal bound for the ReLU FNN for approximating the smooth functions, as the table shows. So this kind of approximation error bound tells us if we want to achieve some desired approximation error, then we know the required width steps and the number of parameters of the model. But this kind of study is still less known for the PQC, or say the quantum model. And today we're trying to solve this problem to try to discover the quantitative approximation error bound for the PQC. And the overall idea is pretty similar to the classical learning theory paper. And the main idea is to say, if we want to approximate a smooth function, then we can use a local Taylor expansion of that function f at some like fixed point, say x naught. And because we know that once we have a local Taylor expansion of like the function at some fixed point, then the approximation is only good when like x is close to that fixed point. So if we want to say use the local Taylor expansion to better approximate the entire function on the entire region, then the idea is to say we can divide the entire region into small local regions. And for each of the local region, we say, like in the first region, we have like a Taylor expansion of fx at some fixed point in that local region. And for each of the like different local region, we have different Taylor expansions for that function. Then we were able to say to have like good approximation on the entire region. So that's the basic idea. And then the next is to use parametric quantum circuit to implement the local Taylor expansion on the entire region. And we divide this entire approach into 3 small steps. The first one is to do the localization. The localization is to like decide the fixed point for the input x, so that we know that for any of the inputs in that region, we can guarantee that the fixed point is always close to the input x. And then we implement each single Taylor term, and then we aggregate Taylor terms together to have this, to have this local Taylor expansion implemented. Okay, so before we proceed, we first introduce basic tools that we will use as a building block of our PQC approximation, which is the data uploading PQCs that we showed before. But as we said, like if we have this kind of complex multi-qubit PQC, it is somehow hard to analyze the performance, and also the construction is not explicit. So instead, we consider like the minimum building block, which is a single qubit data uploading PQC. So if we replace like the multiple one with a single qubit one, we can find that it is actually can be identified with the technique called quantum signal processing, which is widely used in quantum algorithm designs and like Hamiltonian simulations. So once we consider the single qubit case, we set the data encoding gate to be the Rx rotation gate, and let the trainable gate to be the RZ rotation gate. And the result of the quantum signal processing is telling us if we have this kind of circuit, then we can always say implement a polynomial of L degree if we repeat, say, the encoding for L times. And there are extra two constraints for the polynomials, which is that the polynomial should have like the parity constraint, which is L mod 2, and the polynomial should be, say, normalized, which is bounded by 1. And once we have that, we're ready to build our PQC for the function approximation. So as we showed before, we have like 3 mini steps. And the first one is localization. So once we have the entire domain, say 1 to D to D, or 1 to 3, like 0 to 1 to the D, and then we can like divide the entire domain into K to D hypercubes, which means that for each of the dimension, we divide by like each of the like 0, 1 domain, say the integral by uniformly by K. So so in each these kind of K to D hypercubes, we can always find a fixed point in that hypercubes, so that the distance between the fixed point and the any point in that hypercubes is bounded by 1 over D. So here are 2 examples. The first one is the like the one dimension example is the most simple one. So for example, here we set K to be 5, and once we know that X is between 0 and 0.2, then we set point 0 to be the fixed point, so that we know that for any region or any point in that region, the distance between the fixed point and the X is bounded by 0.2. And similar for the like higher dimension case, like the 2D case. So this kind of finding the fixed point approach can be think of like calculating the step function. So once X is between, say, 0 and 1 over K, then we set the fixed point to be 0. So then the rest is just to approximate this kind of step function by the polynomial of a certain degree. And since we see before, the polynomial can be approximated by the single qubit PQC, which means that we can use a PQC to implement this kind of localization step. And the next step is to like construct the single Taylor term use the PQC. The first is to implement the Taylor coefficient. Remember, we see before, we have like K to D hypercubes, which means that we have K to D number of different Taylor expansions, which means we have like K to D different Taylor coefficient. Then we use like K to D number of like rotation gate combined with the selection to implement the Taylor coefficient. And the first register is just to choose like the certain like it's to choose the certain like local regions, and the controlled one is corresponding to the Taylor coefficient. And then the next step is to implement each multivariate monomials and replace x with x minus that fixed point. And this can be simply done by using tensor product between like just a simple cubic PQC that we see before. And then the next is to use linear combinations of unitaries to aggregate all terms together to have the entire local Taylor expansion. And this is the entire PQC for our function approximation. And once we have that down, then we know that the approximation arrow is bounded like with these kind of certain width steps and number of parameters of the PQC. And like finally, we will have the similar non-asymptotic approximation error bound as like the ReLU FN have. Then we are able to compare these two models. And once we set the smooth index to be small and the input dimension d is large, then to achieve the same approximation arrow, then we find the ratio between the size of the like the PQC and the FNN like exponentially decays. So that's a summary of our work. So we like in this work we established the non-asymptotic approximation error bound by explicitly constructing the PQC for the local Taylor expansion, and then we made a comparison with the ReLU FNN. And the future work is to to make a fair and reasonable comparison with the classical machine learning models, and then to find the rigorous quantum advantages. And, yeah.
Awesome. Thanks. Thanks a lot for. Time for a question if Tipara joins us. Oh, awesome.
Yeah, thanks for the talk. So as you may know, the controversial Kolmogorov-Arnold network also has an important component, is actually a BSP line function approximator. So although, I mean, KN faces a lot of criticism from the PIN community, so do you think if we replace that BSP line from the classical KN to a quantum circuit, do you think it will have any sort of advantage compared to classical KN and may have some like real reliable use case in the PIN use case scenario? Sorry.
Yeah, thank you for your question. I think the problem is that when we talk about the quantum model and the classical model, it's kind of like hard to say or define the advantage of the quantum one, the classical, like over the classical one. Yeah. Because now we will not, because even though we show like the size of the like a PQC and the FNN, we'll have like a smaller size for PQC compared to the FNN. We will not say it's an advantage.
Yeah, so because like the actual neuron in the Kolmogorov-Arnold network is also actually a very small size BSP line. So even if I think we could replace those neurons with a single qubit circuit, so and maybe try some like commonly used PIN benchmarks. So say maybe it's kind of a comparable advantage compared to classical ones, probably. It's more like a numerical experiment.
Like you mean just simply consider the number of neurons, or say like the parameters in that model?
Not actually parameters in the model, because we only one qubit to replace the kind. Okay, talk about it later. Right?
Yeah. Yes.
Awesome. Thanks a lot. So thanks very much, and let's thank Zhan again.